Good afternoon, everyone.
Good afternoon, sir.
Okay, so in last class we started our discussion that how we can convert one coordinate system into another coordinate system. So basically representation of vector with respect to one coordinate system into another coordinate system. So there are three formal coordinate systems are available. So that is basically Cartesian coordinate system, and then cylindrical coordinate system, and then spherical coordinate system. So why do you use three different type of coordinate system? Because when we'll try to analyze field, okay, field created by basically the electric field or magnetic field created due to certain geometry. So basically geometry means that the geometry based where the current is basically flowing or basically some certain charge is stored, okay, or maybe you have some time varying charge or basically time varying current is flowing. So in that case, for it is easy to analyze, let's say for example you have a cylindrical wire, okay, you have a cylindrical wire, so it is easy to analyze the field created due to this cylindrical wire using the cylindrical coordinate system. So that's why we basically study different coordinate system. And to understand the field in one coordinate system into another coordinate system, so we need the coordinate transformation. Okay. And before going into coordinate transformation, so in the last class we have already discussed about the coordinate transformation. So you need to understand certain thing. That is basically one is the coordinate variable. So coordinate variable is basically the point. It's basically the point which is located that where we are basically calculating the field. The point where we are calculating the field. Okay, so that is basically coordinate variable. So that may vary. So for different point, it has a different value. Okay, so that is basically coordinate variable. Now the coordinate vector or the basically you can say basically the unit vector system for Cartesian coordinate and let's say for the cylindrical coordinate or spherical coordinate. So they are basically different. So basically you have seen that this coordinate vector are basically formed by rotation of another coordinate vector system. So in that way it is basically work. Okay. So for example, the coordinate variable for Cartesian coordinate system is varies from minus infinity to plus infinity. And similarly, in the y direction, it also varies from minus infinity to plus infinity. And for z coordinate or for basically z variable, it is vary from minus infinity to plus infinity. And any vector v in the coordinate system can be represented as the linear combination of the basis vector. So basis vector you have x, y and z. X, y and z, and these are the basis vector, and this is the strength. Okay, so this is the strength of this vector in the x direction, and this is the strength in the y direction, and this is the strength in the z direction. Okay, so please note that for example, let's say in this point, okay, so consider this point. Okay, so here you have a vector, so it is not necessarily the vector should point in the radial direction. It is not necessarily, the vector may point in any direction. Okay, so vector may point in any direction, so that can be represented as linear combinations. What is the component in the x direction, what is the component in the y direction, and what is the component in the z direction. So these are the magnitude. Okay, so these are basically scalar quantity, ax, ay and az. So they are basically scalar quantity, and x is vector, y is vector, and z is vector. Or in other way, what we can write, that is you have vector v. Okay, so this is basically can be written as this way. So vector means basically this way. So you have V have a x direction, it has some component. Okay, so let's say Vx, or we can write Ax also. Okay, anyway, then you have Vy and Vz. Okay, so this is basically the vector. And when we are writing this way, so it basically mean that it has Ax. X is the scalar quantity and this is the vector. So it is 1, 0, 0. 1, 0, 0 means it is the x vector. Okay, the basis vector plus a y, you have 0, 1, 0. Okay, and then you have a z. Okay, and it is basically 0, 0, 1. Okay, so this basically Vx, Vy and Vz, so this basically indicate the strength. Okay, so this basically in strength in the x direction, strength in the y direction, strength in the z direction, and in this way in a matrix form we can write, okay, the any vector V in a particular point P. Okay, okay, so then it comes to cylindrical coordinate system, but how the cylindrical coordinate system has been formed. So the cylindrical coordinate system has been formed by rotation of our xy coordinate system or xy basis vector. Okay, it has been formed by rotation of our xyz basis vector or Cartesian basis vector. Okay, so here the coordinate variable. So please note that the coordinate variable and the basis vector, these two are two different things. Don't be confused. Okay, so I always tell that don't be confused with the coordinate variable and coordinate basis vector. So they are two different things and two different entity. Okay, so one is basically one basically indicate variable. Okay, so and another is basically one vector quantity and which basically depends upon the position. Okay, the direction basically depends upon the position, but in case of x, y and z it is basically universal, but in case of cylindrical coordinate and spherical coordinate, the direction of the vector is basically depends upon the where is the point where we are basically representing the basis vector. Okay, okay, so rho varies from 0 to infinity, so it's from this 0 and it may goes to infinity and 5. Yes, okay, okay, okay. I need to share this one. Okay. Now, in the spherical coordinate system, it is basically how it has been formed. It has been formed by the rotation of the basis vector. In the cylindrical coordinate system, our basis vector in the three directions. So one is basically rho direction. So it is basically pointing outwards from the cylindrical surface. It is basically normal to the cylindrical surface, and z and phi are basically tangent. Okay, so z is in the z direction and phi or phi is basically in the basically normal to az and a rho. Okay, so it is basically normal to that. So this has been formed by a 90-degree rotation, rotation with respect to z axis. Sorry, 90 degree, 5 degree. Okay, so amount of 5 degree rotation with respect to z axis. Z axis is your center, okay, or the axis of rotation, and that xy plane has been rotated. Okay, so x has been transformed into rho and your y has been transformed into phi. Okay, so in this way, this coordinate transformation has been occurred. So please note that this a rho, a phi, and these are basically different because I have taken this figure directly from the book, and there that they have used some different notation because I want to represent this basically this basis vector in terms of their name only. Okay, so instead of a rho. Okay, so a basically we always try to represent the coefficient. Okay, coefficient of the vector by a rho, a phi, and az. Okay, So that's why there is a little bit mismatch between this figure and the notation. Okay. So here also you can understand that any vector v can be represented. So it has the strength in the rho direction. This is the strength in the phi direction, and this is the strength in the z direction. Okay. So this is basically indicate the strength of the vector. Okay. And we can always write any vector in a, let's say, particular point in terms of its cylindrical coordinate system, okay, or in terms of the spherical coordinate system. The next coordinate system, yeah. So this is the way, okay. This is your z direction, this is your phi, and this is your rho direction, okay. So these are the basically direction. These are not the variable, okay. So please note that. So these are not the coordinate variable. So coordinate variable is different, okay. Always remember. And then it comes to spherical coordinate system. So in the spherical coordinate system, it has three directions, that is r, theta, and phi. So how this coordinate system has been formed? So it has been formed by rotation of z and rho. Okay, the rotation of z and rho plane with respect to phi axis. Rotation of z and rho with respect to phi axis, and z has been transformed into r, z has been transformed into r, and rho has been transformed into theta. Okay, so these are the direction. And it is a little bit difficult to visualize this, but I'll show you some figure later on, but such that you can visualize it in a more proper way. Okay, so this coordinate transform has been occurred by basically rotation of the system, rotation of your cylindrical system, and the axis of rotation is phi axis. The axis of rotation is phi axis, okay, and the amount of rotation is theta degree. Amount of rotation is theta degree, and in which direction? It basically rotate in a, you can say that in a right hand direction. Okay, so it has been rotated in a right hand direction. Okay. Okay, so now it comes to coordinate variable. Okay, so this thing I have already discussed, but again I am discussing because these are little bit difficult thing, and when we'll try to derive one basically how can I say, when we'll try to derive, let's say basically what differential length or differential area or del operator. Okay, so del operator means basically the gradient operator, or basically the divergence operator or curl operator from one coordinate system into another coordinate system. You need to have the knowledge of this transformation. Okay, so although this will not be part of your exam, but you should know that how this is occurring. Okay, so that's why it is very important. Okay, now you are already familiar that rho is nothing, that coordinate variable rho is nothing, basically x square plus y square, square root of x square plus y square. It is basically distance. Rho is basically distance, and phi is what? Phi is basically angle of x plus jy. X plus jy is a complex number. If we consider this is a complex number, then this is phi. Instead of writing tan inverse, you are already aware that why I am not writing tan inverse, because tan inverse may lead to some confusion. Okay. So instead of that, we are writing in terms of complex angle. Okay, so you have a complex number, and if you are able to find the angle of this, then you can easily find out what is phi. Okay, and then in the inverse way, you can write that x is basically projection of rho, the projection of rho with an angle of theta. Okay, so projection of rho. So what is x? X is basically projection of rho with an angle of phi, in the x direction. Okay, so that is basically x, so that is rho cos phi. Okay, and similarly y is equals to rho sin phi, and z is basically z, it does not change. And similarly, from that basically representation of r, theta, and phi in terms of rho, phi, and z, as basically r is basically the distance. R is basically the distance formed by rho and z. Okay, rho and z variable. So the r is the distance formed by rho and z, and you can easily find out that is basically because rho and z are basically orthogonal to each other. Rho and z are orthogonal to each other, or 90 degree to each other. So you can see that this has been formed this can be easily determined, that is square root of rho square plus z square. Okay. Now the theta is the angle which has been formed by, so you can see that z is now your x. Okay, so if you see the similarity between phi and theta, you can see that z is now x and rho is basically y. Rho is basically y. Okay, so you can understand that what is the rotation, how the rotation has been occurred. Okay, so what does it mean by the theta? Okay, theta is basically, we'll see later on that theta is basically this angle. So let's see. Theta is basically this angle. Okay, so this angle. Okay, this angle has been formed by z or z is basically pointing towards the r direction and y is basically pointing towards the theta direction. So in that way it has been formed. Okay, so when this comes to the transformation or basically coordinate variable relationship between the Cartesian coordinate system and the cylindrical coordinate system, it can be written as r is equals to square root of x square plus y square plus z square. Okay, so this is basically also a distance vector. Okay, or not vector, I can say distance variable. Okay, so this is basically the distance variable. And theta is the angle. So how this angle has been formed? So it is basically angle between z and angle. So this is basically the rho. Okay, so the rho can be written in terms of x and y is basically square root of x square plus y square. Okay, so in this way you can find out what is your theta, and phi can be find out that angle x plus jy. And inversely, we need this relationship, that is basically x is equals to r sine theta cos phi, and y is equals to r sine theta sine phi, and z is equals to r cos phi. Why? So r cos theta. So why r cos theta? Because you can see here. You can see here. So here this has been formed. How this has been formed? So this r and this angle is theta. This angle is theta. So if you take the projection, then you will get z is basically is equals to r cos theta. Okay. And one of the important thing is that please remember this relationship. This is not much required most of the cases when you will do the transformation from one to another one system. So this relationship is most important. Okay, this coordinate variable relationship, this one and then this one. Okay, so these two are most important. Okay. Okay, so what we have seen that a vector in Cartesian coordinate. Okay, so you have a vector in Cartesian coordinate, so that can be converted into let's say cylindrical coordinate. So you can find out the basically strength in various directions by coordinate transformation. So before that, how this coordinate transformation works? So you need to understand. So x has been rotated. X has been rotated, y has been rotated, and z has been rotated. So how much is the rotation? The rotation is basically rz. So z is the axis of rotation and phi is the amount of rotation. Z is the axis of rotation and phi is the amount of rotation. And we have seen this rotation matrix for xy plane. So in xy plane, it is easy to visualize this rotation matrix. And if you do this multiplication, it is basically slicing of this matrix, this column. So it is basically slicing this column. And similarly, that if y is rotated, so it is basically slice this column. Okay. And similarly, when z is rotated, so it is basically remains same. Okay. It does not change. Okay. And so finally, what we can write that this rotation matrix is nothing but rho component, phi component, and z component. Please note that this rho component is a unit vector. This rho component is the unit vector in the rho direction. This phi component is the unit vector in the phi direction, and z component is the unit vector in the z direction. Okay. So these are the unit vector in three different directions. Now, if I tell that, okay, so we'll do that later on. Okay, so we don't need right now, but later on we need this unit vector. Okay. Okay, so what we can understand that, let's say you have a vector in Cartesian coordinates, so that is a x, a y, and a z. Okay, so the meaning of this in the cylindrical, you can say cylindrical representation, in the cylindrical representation or cylindrical system is same. Okay, so it is basically you have row vector, and the strength in the row direction is basically a row. Okay, you have phi vector, so it is unit vector, and the strength is a phi. Okay, and you have z vector, and the strength is a z. Okay, and so we know it is basically how this has been formed. So it is a rho, phi, and z. So basically this vector, okay, rz phi into your this column vector. This column vector is basically three different components, and three different components basically indicate the strength in that particular direction, that in the rho direction, in the phi direction, and in the z direction. Okay, so these are the three components. Now, if I try to find out this component values, what we need to do? We need to do inversion. So if I do take matrix inverse in the both the side, then phi rho and z, a phi rho and z, basically strength in three different direction can be find out by this matrix inversion. Now, one of the very important and beautiful property of this matrix is basically it is an orthogonal matrix. It is an orthogonal matrix. So what is the property of orthogonal matrix? The property of orthogonal matrix means basically its inverse is basically its transpose. Its inverse is basically its transpose. Okay, so to do this inversion, you don't need to put any effort. Just do the transpose. Okay, so it is basically this column become this row. You can see that cos pi sin pi. You can see this is cos pi sin pi, and this column become this row. Okay, you can see that is sin minus sin pi and cos pi and 0. And similarly, this row become, sorry, this column become this row. Okay, so it is basically the transpose. Now, if you know that, let's say, how much is the strength in the x direction, how much is the strength in the y direction, and how much is the strength in the z direction, and also you know the point or the position where you need to find out this transformation, then you can easily find out that a rho, a phi, and a z component. Okay. Now, next transformation is cylindrical to spherical. Okay, so before going into the transformation, we need to understand that how this rotation matrix has been formed. Okay, so let's see this figure. Okay, so here you can see that what is this R? Okay, what is the R? So what is the component of R in the rho direction? Can you tell me? What is the component of R in the rho direction?
0.
No.
R
No.
cos theta.
R
Yeah,
sin
cos
theta.
theta. Yeah. This angle is theta. This angle is theta. In the z direction, its component is in the z direction. In the z direction, its component is cos theta. In the z direction, the component is cos theta because this angle is theta. Also, this angle is theta. This angle is theta. Okay. And in the rho direction, this angle is basically 90 minus theta. This angle is basically 90 minus theta. So therefore, in the rho direction, the component of R is basically sin theta. So it is basically component of R in the rho direction. So this is rho direction, and this is your phi direction. This is your phi direction, and this is your z direction. Okay, so you can see this is your rho, then phi, and this is z. Okay, so these are the three directions. In the three direction, you have three components, but you can see that in the phi direction, it does not have any component. R does not have any component in the phi direction. Similarly, what is theta? So this is your theta. Okay, so theta, what is the component in the rho direction? The component in the rho direction. So this angle, how much is this angle? This angle will be theta, because this angle is 90 minus theta, and between R and theta there is a 90-degree angle. Then you can say that between rho and theta, the angle is basically theta. Okay. Between rho and theta, the angle is theta. So you can see it is basically cos theta. Okay. And what is the component in the z direction? Okay. So what is the component in the z direction? So this is basically the component of theta in the z direction. So this is basically minus sine theta. Why? Because it is in the negative direction. Okay, so this is your negative z axis. This is your negative z axis. Then this angle is basically how much? This angle is basically 90 minus theta, and therefore it is sine theta, and the direction is basically minus. Okay, in the negative direction. And you can see that phi has not been transformed. Okay, so phi remains phi axis, because with respect to phi axis rotation has been occurred. So with respect to phi axis the rotation has been, so it does not change. Okay, so it is basically same phi axis. Okay, 0, 1. So 1 basically this is your phi coordinate. Okay, and this is basically 0. This is rho. This point is basically rho, and then you have phi, and then you have z. Okay, so z does not change, and also rho does not change in the formation of phi, because phi axis is remains same, it does not change, only this rotation. And this, if I clamp all these three together, then we form the rotation matrix of r phi. R phi is with respect to phi axis, and amount of rotation is theta. Okay, so this, in this way, this rotation. Now we will apply this concept. We'll apply this concept to find out the coordinate transformation. Okay. So here you can see that A rho, A phi, and Az. Okay, so this is the definition. Okay, A rho, A phi, and Az is basically the rotation matrix. The rotation matrix into AR, A theta, and A phi. Okay. So you can easily understand. This. This is basically strength in the r direction. This is the strength in the phi direction. Sorry, theta direction, and this is the strength in the phi direction. Okay, and this is your rotation matrix, and you can easily convert or obtain this value of AR, A theta, and A phi if you know that value of A rho, A phi, and Az. Okay, by this matrix can be done through the transpose of this matrix, because it is also an unitary or basically orthogonal matrix. Okay, so it is a orthogonal matrix. Okay, now you can see that this column become this row, and this column become this row, and this column become this row. Okay, so in this way it has been done. Next is Cartesian to spherical coordinates. So in this case, so what we have done, so we have considered that x, y, and z, or the Cartesian vector, is equals to your this rotation. You have two rotations. So this is your phi rotation, and this is, then you have a theta rotation. Okay, so phi rotation with respect to z axis, and then theta rotation with respect to phi axis, and then finally you have this. You can say this is the vector. Okay, so vector, or basically the magnitude of the coefficient in the three direction. Okay, so if you do this multiplication, then you will obtain this matrix. And if you want to do the inverse transform, so basically you are doing two matrix inverse. So you are doing this one first. So this this is basically p multiplied. Okay, so this is basically p multiplied before ax, ay, and az. Okay, and then you have a p multiplication of this inverse. Okay, so this is also done, and you can see that this inversion is nothing but basically the transpose. Okay, so you have transpose of the theta rotation. Okay, and if you clamp together, then you will get this value. Okay, and another property is this. You can say this matrix and this matrix are basically, you can say, the transpose of each other. You can easily verify. Okay, so this matrix and this matrix are basically transpose of each other. Okay, because you have done the inversion, and this matrix also possesses the orthogonal property. Okay, so in this way you can transform any you can say any vector in any coordinate system into another coordinate system. Okay. Okay. Now we'll discuss about the vector product, and then we'll move into differential length, differential area, and how that one differential length and area can be converted into another one. Okay, so this is the dot product or inner product. So this is one of the important you can say property of vector. So this basically indicate the projection. Okay, so this is basically related to the projection of one vector into another one. The dot product or inner product u dot v or you can say U transpose into V indicate projection of V on U or projection of U on V. So please note that. So this itself is not the projection. This itself is not the projection. Please note that. So there is a difference. Okay. So there is a difference. Okay. Why? Why it is not itself? Because you have to divide by the unit vector. Because the projection of this is basically the inner product with respect to unit vector in this direction. Okay. The projection of V in the U direction is the inner product of V with respect to the unit vector in the U direction. So what is the unit vector in the U direction? That is U divided by the length of U. Okay, U divided by the length of U. Okay, so here where you can say that this what is the length, you can understand. Okay, and in, let's say, if I want to do the matrix multiplication, it is basically the transpose. You know how to do this kind of matrix multiplication, and it is very easy to perform this inner product. Okay, and U dot V is equals to mod of U into mod of V into cos theta. Okay, so this is the basically you can say that this is the basically the magnitude. Okay, this is basically indicate the magnitude of U dot V, and also please note that it is a scalar product. Please note that it is a scalar product. Okay, so the ultimate the quantity here indicate it is a scalar quantity. Okay, not a vector quantity. And so that's the thing. And then another property is basically this dot product or inner product is basically coordinate transformation invariant. Okay, so this dot product or inner product basically indicates same thing. Okay, so let's say I want to do in the Cartesian coordinate, so it is basically U transpose V, and similarly if I want to do in the, let's say, cylindrical coordinate, that is also U transpose V. Okay, and similarly if I want to do in the spherical coordinate, say in that case also it is U transpose V. Okay, so that's why it is basically coordinate independent. And what I was talking maybe last class, that is component of vector parallel or perpendicular to another vector. So this is very important to understand, that to find out the parallel component. Okay, so let's say I want to find out that you have, let's say, two orthogonal components. Let's say U composed of two orthogonal components. Okay, so that one component is parallel in the V direction. Okay, so parallel in the V direction is basically the projection. If I take the projection of U in this direction, so this vector basically indicate U parallel V. Okay, U parallel V, and rest of the component is basically orthogonal to this one. Okay, orthogonal to this one or basically perpendicular to V direction. Okay, to find out the component parallel to this is basically you have to multiply U with the unit vector in the V direction. What is the unit vector in the V direction? V vector divided by the magnitude of V vector. Okay, into the unit vector in the V direction. So this is a scalar quantity. This is a scalar quantity. Okay, this quantity is basically scalar. Okay, and this is a unit vector in the V direction. Okay, so because we want to find out that component in the V direction, so obviously we need the direction vector of the V. Okay, so this is the direction of V vector of V, and if I substitute this, then distance B into distance B is basically inner product of V with itself. Distance B into distance B is basically the inner product of V with itself. Okay, and this dot product is basically U dot V, and the direction is basically in the V direction. Okay, and if I do in terms of matrix multiplication, then it is basically U transpose V divided by V transpose V into V vector. Okay, so in this way we can find out the component which is parallel to V. Now to find out the component which is perpendicular to V, so what we need to do, we have to subtract the parallel component, because this U composed of two orthogonal components. Na? So U composed of two orthogonal components. One is parallel to V and another is perpendicular to V. Okay, so therefore rest of the components should be perpendicular to V. So I can do this using matrix multiplication in a very easy or a very efficient manner. Okay, so in this way you can easily perform that what is the component that is perpendicular to V. Okay, so if I provide you some let's say some examples, so you can easily understand. So in the last I think last class I have provided one example to how to find out the component parallel and perpendicular to another vector. Okay, so next product is cross product or vector product. So how this look like? So let's say you have two vector A and B. Then the meaning of this cross product is basically the area of this parallelogram. The meaning of this is basically the area of this parallelogram, and it can be easily find out. This area is basically magnitude of A into magnitude of B into sine theta. Now this property is very helpful in finding out area of a triangle. Okay, so let's share this. Okay. Okay, so let's consider you have a you can say 3 point, okay, 3 arbitrary point, and this form a triangle. Okay, so let's say a point P1, P2, P3. So using the cross product, can you find out the area of this triangle? Using the concept of cross product, can you find out the area of this triangle?
Yes, sir. Yes.
Okay, so you can easily find out. So let's consider this is the one vector, this is another vector. Obviously the area of this basically half of the cross product. So area A is equals to half of the, so basically total is the parallelogram, so I don't need the total parallelogram. So half of this is the area of this triangle. So half of the cross product between P1, sorry, let's say P2 minus P1 cross P2 minus P1 cross let's say
P3 minus P1.
Yeah, P3 minus P1. Okay, and take the magnitude because it is a vector quantity. If you do this cross product, it is a vector quantity. Take the magnitude of that. So this is the area of this triangle. Okay, so that's why this property is very helpful in many, let's say, computer graphics problem. And also please note that that rotation matrix, the rotation matrix also play a very important role. So if you take computer graphics in your, let's say, in your future career, so in that case this geometry concept and this basically how can I say, so this geometry concept are very helpful in understanding those subject in advanced level. Okay, so let's answer this one. Okay, and to find out the vector cross product, you are already familiar with how to find out the best vector cross product. So that is very easy and the things to do. So it is basically, if you know the rule of differentiation, determinant of a matrix. If you know the rule of determinant of a matrix, then you can easily find out the cross product between two vectors u and v. Okay, so here x is the direction, or I can say the unit vector in the x direction, y is the unit vector in the y direction, and z is the unit vector in the z direction. Okay, and ux is the component in the x direction, uy is the component in the y direction, and uz is the component in the z direction. And similarly, v has three components. Okay, and if I try to determine the determinant of this matrix, then that is the basically the cross product. Okay, so you know that using cofactor expansion, you can easily find out the determinant of this matrix. So that is basically x into uoi into vz, okay, minus uz into vy. Okay, so in this way you can do it. Okay, similarly for y, so y you have a minus sign, minus sign should be there, and then you remove this, then remove this column. Okay, so just remove this column and think that multiply this ux into vz minus uz into vx. So in this way you can do this, and similarly for the z direction you can find out ux into vy minus uy into vx. Okay, so in this way you can easily perform this thing. But one of the main problem that when you try to implement this using computer, okay, so because most of the nowadays most of the calculation, or basically you can say the problem, are basically solved by computer. Okay, so if you try to implement this using computer, then it is not a good or efficient algorithm. So you need to develop one algorithm such that it can easily provide one vector. Okay, so you have two vector, you have u and v, two vectors are there, and after some multiplication, matrix multiplication, it should provide the output as a vector. Okay, so for that you need to use, for computer implementation you need to use this one, this formula, not that one. Okay, so for computer implementation of cross product you need to use this formula. So here A has three component, 1, 2 and 3. So 1, 2 and 3 can be anything. So x, y and z, or rho, phi, rho, phi and z, or r, theta and phi. Okay, so and anything. Okay. So here that A cross represent a matrix. A cross represent a matrix, and how this matrix has been formed? So this matrix has been formed by taking, this matrix has been formed by this column vector. So how this column vector are formed? So this column vector has been formed by taking cross product, of a vector, cross product of a vector with the unit vector in the x direction, with the unit vector in the x direction and a vector. Okay, so in this way this cross product has been formed, and similarly this column vector has been formed by the cross product of y with a vector. Okay, y with a vector, and this cross product has been formed, the cross product between z and a vector. Okay, in this way these three column vector has been formed, and if you do this matrix multiplication, then you can easily find out the three component of this cross product. Okay. Okay. Now move to vector triple product. Okay. So after vector triple product, we'll discuss about the differential length, differential area, and differential volume. And in the next class, we'll discuss about the Del operator. Okay. Okay. So why do we need vector triple product? Because, for example, you are trying to find out area of a parallelogram. Okay, so for example, let's say
Volume.
Yeah, volume of a parallelogram. Okay, sorry. Mistake. Okay, so you have, let's say you have this particular kind of, let's say, basically a cube formed by parallelogram. Okay, so that if you want to find out the area, sorry, volume of this, so you need, how you can find out? You can find out by taking the cross product. So by taking the cross product between, let's say this is your A and this is your B. Okay, by taking cross product, you can find out the area. Okay, the bottom area. Okay, and then if you multiply this with the height, so how to find out the height? The height is basically the, let's say this is normal. Let's say, for example, this is the normal in this direction. Okay, so I'm just not writing in a proper way. So this is the normal. That is A cross B. Okay, so A cross B. So this is the normal. And let's say in this way, your so this way you have the C. Okay, so this is your C. Then if you take the dot product between these two, if you take the dot product between these two, this vector and this unit vector and this vector, then you will get the component of this component of the, let's say, C, what is basically normal to the surface. The component of C, what is normal to the surface. Okay, so if you take the dot product with this, then it is the basically indicate the volume of this parallelogram cube. Okay, so this is the volume of this. I cannot exactly recall the name, that I think parallel plate or something, parallel piped or something like that. Okay. Okay, so let's share this. Here it is the problem. Okay, so this basically indicates this one, and so based on this property, so it is a volume. So we can form the volume in any way. So we can take the area of any, you can say any cross-sectional area and then multiply with the height. So you can do it anyway. So A dot B cross C is same as B dot C cross A, and that is also same as C dot A cross B. Okay, so these are basically indicate the same quantity. Okay, and another product is vector triple product. Okay, so this is a vector product of two vector B cross C, and that is multiplied with another vector A, and that form another vector. Okay, so ultimately the result is basically vector. Okay, so here the result is scalar quantity, but here the result is another vector quantity. And this property is very helpful when we will try to derive the wave equation. Okay, so when we will derive the wave equation, we need this property. Okay, so when we will derive the wave equation, we need this property, and we will see later on. Okay, and so here this basically indicates B into A dot C, that minus C into A dot B. So the what way to remember this? That is BAC minus CAB. ABC is equals to BAC minus CAB. So in that way you can easily remember this one. And this property can be used. Yes.
Sir, that B is simple multiplication, na? Simple multiplication.
Yes.
B into A dot C.
B into this is a basically scalar quantity A dot C, and basically the need direction is basically B. So here B is the direction of this vector. B is the direction of the vector, and A dot C is a scalar product, na?
Yes, sir. Yes.
A dot C is a scalar product. So scalar, if you multiply P or post, it is same, na? If you multiply here also or here, it is basically same. Basically scaling. Multiplying a vector with scalar is basically scaling of the vector. Okay. And similarly, So you can see it is basically the resultant direction. So okay, another thing is, please remember the resultant direction of this vector is basically b minus c. Obviously some multiplication with b. Okay, some scalar scaling of b and scaling of c, and then difference between them. Okay, so this is the resultant direction, and based on this property, so we can find out this quantity. So it is very helpful when we will try to derive the wave equation. Okay, so that is basically del cross del into field is there. Okay, so f is certain vector field, that is equals to del of, so the same thing, so del of, so it is basically the b. Okay, this one, del of a dot c. Okay, so you can see that that is basically del dot f. Okay, minus a dot b. So a dot b means del dot del into f. So del dot del is basically the Laplacian operator, del square. So this property is very helpful. So I will see later on that this this will vanish and this will also vanish, and we'll see some that del square f is equals to 0 or some constant. Okay, so from there we can easily find out the wave equation. We'll see later on. Okay, so then another product that is available. So this property is not important because we don't need this one. Okay, so we may skip this one. Okay, so that's all from this side. And now actually I have not prepared this slide. Okay, so I'll start the differential length from this slide and then I'll show you how to derive this one. Okay, is it visible, or shall I make it zoom a little bit? Is this visible to you?
Yes, sir.
Yes, sir. Yes, sir.
Okay. Okay, so here now we move into calculus. Okay, so previously we were basically dealing with simple algebra, vector algebra. Now we move into vector calculus. Okay, so in the vector calculus, at the first element you need, that is basically differential length. Okay, then you need differential area and then differential volume. Okay, so these are the three fundamental quantity you need to understand the vector calculus. Okay, the first is basically the differential length. Okay, so that is basically dl. So dl can be anything. So that is, let's say for example, how this dl look like. So for example, here in the Cartesian coordinate system, you have a dl. So L is a vector, so that is in the x direction. X direction you have a vector and dx into, so instead of ax we will write that x hat. Instead of ax you can write x hat, because based on my notation that it should be x hat. Okay, so you can see that this dl, so it is a vector quantity and also a differential length. So it is an infinitely small length and also it has a direction. It is a infinitely small length and it has a direction. Okay, and same way you can have the direction vector in the, or say differential direction. Okay, differential direction in y direction and similarly in the differential direction in the z direction. Okay, so differential length in the z direction. So the resultant is basically sum of them, sum of these three. Okay, so if I find out the neat direction, it may point out some in the diagonal of the cube. Okay, so if I find out the neat direction of this differential length, so that will basically point out in the diagonal direction. Okay. Okay, so this is our definition of differential length for the general purpose. Okay, so this is the differential length for the general purpose. Okay, so that is dx into x hat plus dy into y hat plus dz into z hat. Okay. Now in the cylindrical coordinate, the definition is a little bit different. Okay, so this definition and this definition are interrelated. How this definition is coming? Okay, so that thing I'll try to derive in this class, and rest of the thing you'll do by yourself. Okay, so let's find out how this derivation is coming. Let me share. So you have dl vector is equals to x vector comma y vector comma z vector into dx. So please note that these are the variable, and this is not, this is are basically vector. So don't be confused in dy and dz. Okay. Okay. So what is x, y, and z? So x is nothing but 1, 0, 0. What is y? Y is 0, 1, 0. And what is z? 0, 0, 1. Okay. And dx, whether the time is up now. So I'm giving you a hint, so please try by yourself, and then in the next class we'll discuss. So dx is basically, how can I write that? X is equals to rho cos phi. Then dx is equals to, or you can say the del x. Okay, so the dx is equals to del rho or d rho cos phi minus d phi rho sin phi, because the derivative of cos is this one, and then dy is equals to d rho sin phi plus d phi rho cos phi. Okay, so this thing I can write as d rho d phi d z, and here you have cos phi minus rho sin phi minus rho sin phi, and then 0. Then you have sin phi rho cos phi 0, 0, 1, 0, and this thing you need to write in this form: rho phi z into transpose of this. So rho phi z, you know. So this, what is this? This is the rotation matrix. So this is basically the transpose of this rotation matrix, and that is coming how much? Cos phi cos phi, the transpose of the rotation matrix. Okay, so cos phi, sin phi 0, and then sin phi, so there is a minus sin phi cos phi 0, 0, 0, 1. Okay, so this into this matrix, into this vector, and if I do this multiplication, then you have rho phi and z. Okay, and then if I do this matrix multiplication, then you will get basically sin theta, that is 1 rho 0, this will be 0, 0, 0, 0, 0 into d rho d phi dz. So in this way you can derive it. In the next class I will discuss this in details. Okay, so goodbye for now, see you in the next class. So do you have any question or query? Please let me know.
No, sir.
Okay.